Welcome to Module 4, Dynamics, Forces and Newton's Laws of Motion. I'm Dr. Antam's virtual teaching assistant. In this lesson, we'll connect how forces cause changes in motion, interpret common forces like normal force, tension, and friction, and practice drawing accurate free body diagrams to solve problems systematically. This module is part of the Algebra-Based College Physics 1 course by Dr. Moses Antam, Associate Professor of Physics. A force is essentially a push or pull, characterized by both magnitude and direction, making it a vector. In physics, we measure force in SI units called newtons. Since forces are vectors, we must use vector addition methods to combine them. Module 3 introduced graphical and analytical methods, which we'll apply to solve problems involving force addition. We'll rely on the analytical component method, resolve each force into x and y components, apply sign conventions, then sum components to find the net force. That net force drives acceleration. Newton's first law, or the law of inertia, states that a body at rest stays at rest, and a body in motion continues at constant velocity unless acted upon by a net external force. This law highlights the necessity of a net force to change an object's velocity. Let's explore mass versus weight by comparing a kilogram of cotton balls and a kilogram of gold. Which has more mass? The answer might surprise you. Both the cotton balls and gold have the same mass, as mass is a measure of the amount of matter in an object, regardless of its material composition. Mass is the measure of the amount of stuff or matter in an object, determined by the number of atoms and molecules it contains. It remains constant regardless of location, measured in kilograms. Weight is the force of gravity acting on an object, calculated as mass times the acceleration due to gravity. On Earth, this is approximately 9.8 newtons for a 1 kilogram object. While mass remains constant, weight can change with varying gravitational forces. For instance, the Moon's gravity is weaker than Earth's, affecting the weight of objects differently. Newton's second law states that acceleration is directly proportional to the net external force and inversely proportional to mass. This relationship is expressed in the equation net force equals mass times acceleration. Newton's third law of motion emphasizes symmetry. When one body exerts a force on another, the second body exerts an equal and opposite force. This principle is famously summarized as for every action, there is an equal but opposite reaction. When objects rest on a surface, the surface applies a normal force supporting the object's weight. On a non-accelerating horizontal surface, this force equals the object's weight. On inclined planes, the weight of an object can be resolved into components parallel and perpendicular to the surface. These components help calculate the normal force acting on the object. Tension force is the pulling force along a stretched connector like a rope or cable. When supporting an object's weight, the tension equals the object's weight. Friction is a contact force opposing motion between surfaces. It includes static friction for stationary surfaces and kinetic friction for moving surfaces, both proportional to the normal force. A free body diagram visually represents all forces acting on an object, using vectors extending from a dot. It helps resolve forces into horizontal and vertical components for analysis. This diagram shows a box at rest on a horizontal surface, illustrating the forces acting on it, including the normal force and weight. On a rough inclined plane, the free body diagram depicts forces like static friction and normal force, with weight components parallel and perpendicular to the surface. This detailed diagram further breaks down the forces acting on a box at rest on an inclined plane, using trigonometric functions to resolve weight into components. A clock suspended in air using a string is shown in this diagram, highlighting the tension force and weight acting on it. To solve problems involving Newton's laws, follow these steps. Sketch the problem, identify knowns and unknowns, draw a free body diagram, apply Newton's second law, check for acceleration, and verify your answer for reasonableness and unit accuracy.